Everything in the universe is in motion. From the tiniest subatomic particles to the grandest galaxies, nothing stands still. This constant movement is a fundamental part of our existence, but how do we understand and measure this motion? That's where momentum comes in. In physics, momentum is a measure of a moving object's tendency to stay in motion. Imagine a speeding train. It has a lot of momentum because of its mass and velocity. We can calculate momentum using a simple equation. P equals m times v. Where p is momentum, m is mass measured in kilograms, and v is velocity measured in meters per second. Momentum is measured in kilogram meters per second. It's a vector quantity, meaning it has both magnitude and direction. Momentum is everywhere in our daily lives. It's a fundamental concept that governs the motion of objects, both big and small. From the bustling streets filled with people to the flowing rivers and the ceaseless movement of traffic, momentum is at play in every corner of our world. Consider a car speeding down the highway. The faster it goes, the more momentum it builds up. This momentum is a product of both its speed and its mass. The faster it goes and the heavier it is, the more momentum it possesses. This is why a heavy truck barreling down the road has significantly more momentum than a small car traveling at the same speed. That's why a small car at a low speed is less dangerous than a large truck at a high speed in a collision. The truck's greater mass and speed mean it has more momentum, which translates to a greater force during impact. The truck's greater momentum means a larger force is involved in a crash. This is why truck accidents can be so devastating, requiring significant emergency response efforts. Think about a game of bowling. When you roll a heavy bowling ball down the lane, it gains momentum as it picks up speed. A heavy bowling ball rolling down the lane has significant momentum, which is why it can knock down those pins with such force. The combination of its mass and velocity makes it a formidable force. The heavier the ball and the faster it rolls, the more pins it's likely to topple. This principle of momentum is what makes the game both challenging and exciting. Even in space, momentum reigns supreme. Objects in space like satellites and space shuttles rely on momentum to maintain their orbits and navigate the vast expanse. Comets, for instance, travel at incredible speeds as they orbit the sun. Their momentum carries them through the solar system, dictating their paths and interactions with other celestial bodies. Their momentum is a testament to their mass and velocity. The sheer speed and mass of a comet give it the momentum to travel vast distances, showcasing the power of this fundamental force in the universe. One of the most fundamental laws in physics is the law of conservation of momentum. This law states that in a closed system, the total momentum before an interaction is equal to the total momentum after the interaction. In simpler terms, momentum cannot be created or destroyed, only transferred. Imagine two billiard balls colliding on a pool table. Before the collision, each ball has its own momentum. During the collision, they exert forces on each other, and their velocities change. However, the total momentum of the system remains the same. This principle is crucial for understanding collisions of all kinds. Let's put our momentum knowledge into practice with a simple example. Imagine a 0.5 kilogram soccer ball traveling at 10 meters per second. What is its momentum? Using the equation P equals m times v, we can easily calculate the ball's momentum. P equals 0.5 kilograms times 10 meters per second, which equals 5 kilogram meters per second. This means the soccer ball has a momentum of 5 kilogram meters per second. This value represents the ball's tendency to stay in motion. A larger, faster-moving object would have a greater momentum. Section 5. Elastic versus inelastic collisions, bouncing back or sticking together. This section delves into the fascinating world of collisions, exploring how different types of collisions behave under various conditions. Not all collisions are created equal. Some collisions result in objects bouncing off each other, while others cause them to stick together or deform. We can categorize them into two main types, elastic and inelastic collisions. Each type has unique characteristics and outcomes. Elastic collisions. In an ideal elastic collision, both momentum and kinetic energy are conserved. This means that the total energy and momentum before and after the collision remain the same. Imagine two billiard balls colliding head-on. This is a classic example of an elastic collision. They bounce off each other with no loss of energy. The kinetic energy and momentum are transferred from one ball to the other, allowing them to continue moving. In reality, perfectly elastic collisions are rare, but many collisions are close enough to be considered elastic. For instance, collisions between atoms in a gas can often be approximated as elastic. Inelastic collisions. In an inelastic collision, momentum is conserved, but kinetic energy is not. This means that while the total momentum of the system remains constant, some of the kinetic energy is lost. Some of the kinetic energy is transformed into other forms of energy, like heat or sound. This transformation is why inelastic collisions often result in objects sticking together or deforming. Think about a car crash where the vehicles crumple upon impact. This is a prime example of an inelastic collision. The energy used to deform the cars is a sign of an inelastic collision. The crumpling of the metal absorbs energy, reducing the kinetic energy of the system and protecting the occupants. Understanding the differences between elastic and inelastic collisions helps us design safer vehicles, better sports equipment, and even understand the behavior of particles at the atomic level. The principles of these collisions are fundamental to both everyday experiences and advanced scientific research. Section 6. Impulse, the force of change. So far we've explored momentum as a measure of an object's motion, but what causes momentum to change? The answer is impulse. Impulse is the change in momentum of an object. It's closely related to force and time. A large force applied over a short period can have the same impulse as a small force applied over a long period. We can calculate impulse using the following equation, J equals F d tot, where J is impulse, F is force measured in newtons, and dt is the change in time measured in seconds. Impulse is measured in Newton seconds, which is equivalent to kilogram meters per second. Section 7. Force, time, and momentum's transformation. The relationship between force, time, and momentum change is crucial. A small force applied over an extended period can produce a significant change in momentum, just like a large force applied for a short time. Think about a car airbag during a collision. The airbag increases the time over which the force of the impact is applied to the passenger. This extended time reduces the force experienced by the passenger, decreasing the risk of severe injury. This principle is also essential in sports. A baseball player hitting a home run applies a large force to the ball for a fraction of a second, resulting in a significant change in the ball's momentum. Section 8. Momentum's everyday wonders. Momentum is more than just a physics concept, it's a fundamental principle that governs the motion of objects and is deeply embedded in the fabric of our everyday experiences. It plays a crucial role in countless aspects of our daily lives. Whether we're walking down the street, cycling to work, or driving a car, momentum is at play. From the design of safety features in cars to the understanding of rocket propulsion, momentum is a fundamental principle that shapes our world. Engineers and scientists rely on the laws of momentum to innovate and create technologies that enhance our safety and expand our horizons. Car safety, as mentioned earlier, car safety features like airbags and crumple zones are designed to manipulate momentum and impulse to minimize injury during collisions. These features absorb and redistribute the forces involved in a crash, protecting the occupants. Rocket science. Rockets use the principle of conservation of momentum to propel themselves upward. This principle is crucial for space exploration, allowing us to send satellites, probes, and even humans into space. The rocket expels hot gas downward, and in return, the gas exerts an equal and opposite force on the rocket, propelling it upward. This action-reaction force is a direct application of Newton's third law of motion. Sports momentum is a key factor in many sports, from baseball to tennis to bowling. Athletes harness momentum to enhance their performance, whether it's hitting a home run, serving a powerful tennis ball, or delivering a perfect bowling strike. Athletes use their understanding of momentum to maximize their performance and achieve their goals. By mastering the principles of momentum, they can improve their techniques, increase their efficiency, and gain a competitive edge in their respective sports. Section 9. Key takeaways, embracing the momentum mindset. In conclusion, momentum is a fundamental concept in physics that helps us understand and explain the motion of objects. From the smallest particles to the largest celestial bodies, momentum is a universal language that governs the universe's movements. By grasping the principles of momentum, impulse, and the conservation of momentum, we gain a deeper appreciation for the intricate workings of our world and empower ourselves to solve complex problems and make informed decisions in various fields.